The red object you're seeing in this image could be the farthest galaxy found to date. The light from this galaxy has traveled about 13.5 billion years to reach us. So we are looking at the most distant starlight anyone has ever seen. It's like looking at the dawn of time. Astronomers discovered this blurry galaxy using the James Webb Space Telescope's early release science program. This baby galaxy has revealed some of the most intriguing secrets of the early universe. But how did scientists calculate the distance to this galaxy? Is this really the most distant and the youngest galaxy found to date? Finally, and most importantly, what can we expect from the future deep space observations by the James Webb Space Telescope? Looking deep into space is like peering back in time. If we see a galaxy whose light travel distance is 13 billion light-years, we're actually looking at how the galaxy appeared 13 billion years ago. Astronomers have seen dozens of galaxies that existed at least a billion years after the Big Bang. But the first few 100 million years of the universe remain an uncharted epoch. In fact, it is the last significant unexplored era in the history of the universe. So far, we have found just 3 galaxies in that epoch, and only one has been spectroscopically confirmed. One of the most established methods to find distances to deep space galaxies is measuring the amount of redshift. The universe has been expanding ever since the Big Bang, a process that stretches light into longer, redder wavelengths. Starlight from distant galaxies leaves its source as visible light, but by the time it reaches us, it is redshifted down the electromagnetic spectrum into the infrared range. Invisible to our eyes, but perfect for Webb sensors, astronomers know that the redder light is, the farther away the galaxy that produced it. Spectroscopic redshifts involve analyzing the spectral lines observed in distant galaxies and comparing them with those we observe on Earth. Redshift can be represented by a dimensionless number, z. Z equals 0 denotes present time, and as its value increases, so does the look-back time and the distance to that object. But it's important to note that this is only valid for objects in deep space. For example, the neighboring Andromeda galaxy is moving towards us, so it has a blue-shifted spectrum. The look-back time of Andromeda is 2.3 million years. Only one galaxy has been spectroscopically confirmed in the era of Z greater than 10, the first few 100 million years after the Big Bang. It is the galaxy GNZ 11, a red smudge seen as it appeared 13.4 billion years ago. Although deep space observations with the Hubble Space Telescope have pushed our cosmic horizon to within the first 500 million years after the Big Bang, galaxies at redshift more than 12 cannot be observed with Hubble. That's because of the limit of its wavelength coverage at 1.6 micrometers. But thanks to Webb's extremely sensitive NIRCam instrument, we now have an unprecedented view of the universe at 2 to 5 micrometers. This opens our window to the Z greater than 10 epochs of the cosmos. In the new research paper, astronomers have analyzed 2 remarkably luminous galaxy candidates between Z equals 11 and 13, as revealed by Webb. The analysis is based on some of the first NIRCam datasets observed and released over extragalactic fields. In particular, they focused on 2 early science programs, GLASS and SEERS. The team first found all the objects having photometric redshifts greater than 10. Then they inspected images of every candidate source to note diffraction spikes or contamination from neighbors. Finally, they found 5 plausible Z greater than 10 candidates that survived all the conservative checks. The researchers analyzed 2 of these 5 candidates in their paper, GLZ 11 and GLZ 13. Out of these 2, GLZ 13 is the one having the maximum redshift of around 13.1. This means the galaxy existed when the universe was just 300 million years old. And the most interesting thing about this galaxy is its stellar mass, around 1 billion solar masses. That's comparable to that of GN-Z11, the record holder of the farthest galaxy found and confirmed spectroscopically. The fact that the stellar mass of this galaxy is of the order of 1 billion solar masses indicates that star formation took place quickly in the early galaxies. Or maybe producing massive stars is far easier than scientists have predicted. Or perhaps the very earliest galaxies were shaped by gravitational forces we don't understand. These 2 luminous objects place novel constraints on galaxy evolution in the cosmic dawn epoch. Moreover, they indicate that the discovery of GN-Z11 back in 2015 was not simply a matter of good fortune. Instead, there is a likely population of UV luminous sources with a very high star formation rate. Although the discovery of GLZ13 in the early data release demonstrates the true power of Webb, there is an interesting point to note. This scatter graph from the team's research paper shows the brightness of all the known galaxies in the first billion years of the universe. The lower the absolute magnitude, the brighter the galaxy. And, of course, the more the redshift, the farther the galaxy is away from us. As you can clearly see, GLZ13 is not the one having maximum redshift. This record is held by another outlier, named HD1. HD1 was discovered in April 2022 by ground-based telescopes. The galaxy existed in the first 300 to 400 million years after the Big Bang. Early analysis shows that HD1 could either be a starburst or a quasar. If it is a starburst, the star formation rate must be around 100 solar masses per year, which is about 30 times that of the Milky Way. But if it is a quasar, its supermassive black hole must have a mass of about 100 million solar masses. So the black hole must have grown from a gigantic seed in the first few 100 million years of the universe. Given the epoch we are discussing, this poses a problem to the current black hole models. The problem with HD1 and GLZ13 is that they haven't been confirmed spectroscopically. This technique is the gold standard in determining extragalactic distances, so Webb will have to perform a detailed analysis of these galaxies to determine an accurate redshift value. Either of them could win the title of the farthest galaxy found to date. However, the glory will be short-lived. With Webb working at full capacity, astronomers expect hundreds of galaxies to be discovered at such distances within a year. Who knows? We may have new candidates by next week. The future of extragalactic astronomy appears promising in the James Webb era. It will be interesting to see what those distant galaxies are made of, how much dust they contain, and the story of the brilliant stars within. We're only just starting to get familiar with the universe's most ancient light, even though it's been out there all along. This concludes the 18th episode of the Sunday Discovery series. If you enjoyed this video, make sure to like it, subscribe to our channel, and press the bell icon so that you don't miss future episodes of this series.